The enormous explosion is an idea that has shaped how we might interpret the cosmos, outlining the foundation of modern cosmology based on Einstein's theory, also referred to as textbook cosmology. The Great Explosion was the moment when the universe began its expansion, signaling the formation of all matter, energy, and existence. This event occurred approximately 13.8 billion years ago and led to the vast universe we observe today. However, recent developments in cosmology imply that the Great Explosion probably wasn't the absolute beginning. Instead, there might have been a phase prior to the massive blast that was equally crucial in shaping the universe as we know it. This earlier period is known as cosmic inflation. Inflation is perhaps one of the most fascinating aspects of modern cosmology. It suggests that before the hot, dense time of the Great Explosion, the universe underwent an extraordinarily rapid, dramatic growth. During this phase, the universe was increasing in size at an astonishing rate. To illustrate how extreme this expansion was, if the universe began smaller than an atom, it would have expanded to be incomprehensibly larger than the entire observable universe in a tiny fraction of a second, around 1/4 of a second. This inflationary stage didn't last long, but played a vital role in shaping the universe. Once the inflationary period ended, the energy driving this expansion was released into space, warming it and creating the particles of matter that make up everything we observe in the universe. In many ways, inflation is the precursor to what we call the Great Explosion. While the theory of inflation is widely accepted in cosmology today, many unresolved questions remain. For example, we don't yet understand what triggered inflation, what caused it to end, or how long it lasted. These are open questions in cosmology, and answering them is important for a deeper understanding of the origins of the universe. Prior to inflation, the universe was in an extraordinarily dense, compact region of matter, often referred to as a singularity. From this singularity, inflation began and eventually led to the formation of atoms, particles, stars, and planets. The concept of the Great Explosion as the beginning of everything is captivating, but modern cosmology suggests a more intricate picture. Some theories propose that the universe underwent a phase before the massive explosion. During this phase, inflation caused the universe to grow at a remarkable rate, expanding in size by nearly 1 trillion times in a fraction of a second. This rapid expansion was driven by a strange form of energy that permeated empty space. When inflation ended, the energy that had powered this growth was transformed into particles, warming the universe and triggering the hot, dense state we refer to as the Great Explosion. This inflationary stage was cold and empty, but set the stage for the creation of matter and the universe we observe today. One of the more speculative ideas in modern cosmology is the concept of eternal inflation. This theory suggests that inflation did not shut off at once, but rather stopped in patches, creating a variety of bubbles, each of which could be a universe of its own. Our universe would be just one of these bubbles. According to eternal inflation, there could be an infinite number of such universes, each with its own set of physical laws and constants. This is where the idea of the multiverse becomes significant. The notion that our universe could be one of many, or even an infinite number of universes. If this concept proves true, it would explain why our universe is so perfectly suited for life. In this multiverse scenario, every possible combination of physical laws could exist in different universes, and we happen to live in one where conditions are ideal for stars to form and for carbon, oxygen, and other elements essential for life to exist. While theories like eternal inflation and the multiverse speculative, the idea of inflation itself is grounded in observational evidence. The strongest support for inflation comes from the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMBB was emitted about 380,000 years after the Great Explosion, when the universe had cooled enough for atoms to form. At this point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially capture a snapshot of the early universe. The light provides clues about the universe's earliest moments, helping researchers understand what occurred shortly after the Great Explosion and supporting the inflationary model. One of the most important discoveries came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These images show subtle variations in the temperature of the early universe, and these variations match the predictions made by inflationary. This empirical evidence reinforces that inflation is not just a theoretical idea, but a key part of how we understand the universe's origins. Understanding the Great Explosion and what preceded it requires combining two of the major theories in modern physics: Einstein's theory of general relativity and quantum theory. General relativity explains the large-scale structure of the universe, including the behavior of galaxies, stars, and planets, while quantum theory explains the behavior of particles at the smallest scales to address the fundamental questions in cosmology, such as what the universe is made of and where it originated. Scientists must develop a theory that unifies these two frameworks. This would allow us to understand not just the Great Explosion, but also the conditions that led to it. One of the most astounding aspects of the universe is its size. The most distant objects we can observe are approximately 47 billion light-years away, meaning the observable universe spans roughly 94 billion light-years across. This may seem odd given that the universe is only 13.8 billion years old. How can the observable universe be larger than the time it would take light to travel across it? The answer lies in the fact that the universe has been expanding over time. As the universe expands, the distance between objects increases, causing distant objects to move further away than the time it would take light to reach us. Most scientists believe that the universe stretches far beyond the observable universe. In fact, it's possible that the entire universe is infinite in size. The observable universe is essentially the portion we can see, limited by how long light has had to travel since the Great Explosion. There may be vast regions of the universe that we will never be able to see. While it's possible that the universe is infinite, the question remains, is there anything beyond the universe? Most scientists are somewhat uncertain about this idea. If the universe is infinite, there is no outside to it. The universe would simply continue forever. Even if the universe is finite, it may not make sense to talk about anything beyond it. Beyond would imply something outside of space, which itself is a property of the universe, so the concept of beyond the universe may not have any physical significance. Just as the origin of the universe is a topic of great study, so too is its ultimate fate. The best current estimate is that the universe will continue to expand forever. This is due to a mysterious phenomenon known as dark energy, which is causing the universe's expansion to accelerate. Before the discovery of dark energy, scientists believed that the expansion of the universe would eventually slow down due to the gravitational pull of matter. There was even a possibility that the universe could stop expanding and begin contracting, leading to a big crunch. However, dark energy seems to be pushing the universe apart at an increasingly fast rate. If this acceleration continues, the universe will keep expanding indefinitely, eventually reaching a state where galaxies are so far apart that they are isolated from one another. In this scenario, the universe would become cold, dark, and desolate. Stars would burn out, planets would drift apart, and matter would eventually decay. This is referred to as the Big Freeze or heat death of the universe. The story of the universe from the Great Explosion to its possible end is one of the most important and complex narratives in science. While we've learned a tremendous amount about the origins of the universe through the theory of inflation and the study of the cosmic microwave background, many questions remain unanswered. What caused inflation to begin and end? What lies beyond the observable universe? Is there a multiverse? And if so, how many other universes exist? As scientists continue to study the universe using advanced technology and theories that unify quantum mechanics with general relativity, we will undoubtedly gain deeper insights into these mysteries. The pursuit of understanding the universe is ongoing, and each discovery brings us one step closer to answering the ultimate questions about our existence. The study of the universe's origins and structure is not only a scientific endeavor, it also raises philosophical questions about existence, reality, and our place in the cosmos. One significant area of interest in cosmology is the nature of dark matter, which is believed to make up around 27% of the universe's mass energy content. Unlike normal matter, dark matter doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Understanding dark matter is essential for explaining the formation and behavior of galaxies. Ongoing studies and observations have provided insights into dark matter's properties, but its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and other exotic particles. However, to date, no direct evidence of dark matter particles has been found. The search continues through a combination of terrestrial experiments, astrophysical observations, and simulations that model how dark matter affects the large-scale structure of the universe. Another key area of research is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy accounts for approximately 68% of the universe's total mass energy content. Its discovery was unexpected and has led to numerous hypotheses, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is crucial as it will determine the ultimate fate of the universe. Researchers are studying its effects on cosmic structures and trying to determine whether it remains constant over time or evolves. In addition to dark matter and dark energy, the study of large-scale structure formation offers profound insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have revealed how matter clumps together, influenced by gravity, leading to the complex patterns we see today. Simulations run on supercomputers help scientists understand how these structures formed over billions of years and continue to evolve. Astrobiology, too, intersects with cosmology as researchers seek to understand the conditions necessary for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has accelerated with thousands discovered in recent years. Some of these exoplanets lie in their stars' habitable zones where conditions might be suitable for liquid water to exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet hospitable to life. Finally, the role of fundamental physics in cosmology cannot be overstated. The quest for a unified theory that combines general relativity and quantum mechanics continues to challenge physicists. Theories such as string theory and loop quantum gravity aim to bridge these two realms, offering explanations for phenomena like black holes and the early universe. As technology advances, so does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are transforming our understanding of the universe, providing unprecedented detail of distant galaxies and cosmic events. With each groundbreaking observation, we move closer to unraveling the mysteries of the universe's formation, evolution, and ultimate fate. The exploration of the universe is a rich tap of scientific inquiry and philosophical reflection, from the fundamental forces that shape large-scale structures to the search for extraterrestrial life. Our investigation is a testament to humanity's unyielding, deep curiosity about the cosmos. As we strive to answer these profound questions, in doing so we gain a greater appreciation for the vastness and complexity of the universe.